All right, welcome back, everybody. Looking forward to the next talk. Will be about hacking electronic shelf labels. And with me on stage is Jakob, Marius, and Konrad. Please give a warm round of applause, and the stage is yours.
Okay. Yes, thank you for introducing us. Thank you for being here. We are very grateful to be here and to share our journey of reversing electronic shelf labels with you. First, some words about ourselves. We are all three students from the university in Darmstadt, and yeah, the name is already told. To motivate for our research, think of the following. I think it's not too complicated, so it's hot outside and you want to cool down yourself. So what you can do is eat delicious ice cream, and for that, get into your favorite grocery store. Run around and locate the ice cream, and then you'll find out, that's very expensive and the prices might went up since last week, and that happens quite often. So you might think at that moment, I'll go home and do the ice cream by myself. When we saw that as curious IT security students, we thought, okay, that shelf label went digital, but what could go wrong when you place this into a system? What kind of attack vectors might arise? Are we able to change the price and then maybe get cheaper ice cream at checkout? So some words about electronic shelf labels, what they are. I already said they are coming more and more often, and they replace this classic version of a shelf label. They bring some benefits because you might save material. When you change something, you can do that more flexible, and you also have the possibility to do that remote and set up a schedule. For example, make alcohol more expensive on Friday evening or so. They come in different versions, so that depends on how you talk to these shelf labels. Some are accessible via Bluetooth, and some others are accessible via 2.4, a protocol around 2.4 gigahertz, and then they communicate with an access point, but more on that later. And they have a battery inside, so they can be drained, and then you have to replace it. And they also have a MAC address, which in theory should be unique to identify them. Our talk is mainly split into two parts. So we analyzed the tags of two vendors, and then the first vendor only had these tags that communicate via Bluetooth, and then the second one also had tags that communicate via a different protocol around 2.4 gigahertz, and there we also had access to an access point. Then we have some takeaways in the end, what we learned during this long journey. And the first chapter, or the first vendor, calls himself PickSmart. We would leave the smart away here, as you will see in the next minutes. They did some things that were not super smart, but they are a vendor for ESL tags coming out of China. They advertise themselves with smart management warehouse systems and wireless IoT, and they also advertise with a lot of customers. You might know some of them. We have some pictures here. Yes, and for the next part.
Perfect. Of course, they're also certified by TÜV Rheinland, at least their manufacturing process. So that's quite nice to advertise, I would say. But let's look how verified they are really. So we received this beautiful access point, beautiful price tag there, and an Android application. Just registered ourselves to the application, opened the app, and just found every price tag in our proximity, which is quite nice, usability-wise. And then, we looked at the infrastructure. And we have this phone in the center where you can install the Android app and then talk to the ESL tags via Bluetooth Low Energy. And then we have the web server, where there's some management functionality there, where you can manage some products maybe and stuff like that, and you can talk to that via HTTP. So let's first start by looking at the BLE connection. To do that, we of course have to open up the app, click on a price tag, change something, and then click on this beautiful display button there to sync the changes onto the price tags. And then next we can just open our Wireshark and look at the connection that's being sent back and forth. And of course, that's not really like nice to look at, so we created some flow graph with the bytes that are being sent back and forth, and of course, that doesn't really help. So we have a more broader overview or a more simpler view, but still we need to now maybe start with some educated guesses on what we might see here. First, we might have some page size that is exchanged. So Bluetooth Low Energy has, of course, a very limited amount of data that can be sent back and forth in one message. We might have a total size that has been sent, or that can be sent via the image, for example. And then maybe there's some paged data that is being sent. So for example, when we split up the image in certain blocks, we then send all these pages separately. And probably some acknowledgements and something similar, because the comment byte might be pretty similar. And then, of course, what we did is we tried to reverse engineer the protocol by looking at the application, so to understand what the bytes really mean. And we started by just downloading the app, use JetX to transfer or generate readable Java code from that, so that we can really look into it more easily. And then found an entry point in a manifested file and found out it's Flutter, which makes it most of the time is a little bit harder, but still we went for it. A short word on Flutter, it's like this open source framework where you can create multi-platform apps, so that you don't have to manually write the same code for each app or for each platform. You can just use Flutter and compile your Dart source code into ARM instructions and then include this library into the application you want to use. Then we have this unreadable assembly data in there, but luckily for us, the Bluetooth communication at first was just readable in a Java code, so we could just use that. But the REST API, sadly, was in the Flutter part. And then we started reverse engineering, and reversed the protocol by looking through all these Java classes. And so what we found is first, like we guessed correctly, the block size is requested, sent back. Then we will we will now transmit the image, for this example, maybe 4,000 bytes. Got acknowledgement, then say again, now we will really transmit the image now. Click OK again, and then we just send the pages until the end, and then get the acknowledgement I just mentioned. So most of you might see that there's a problem. We don't have any authentication currently, so that's maybe not that fine. It's nice for usability maybe, so that you can just open the app and use it, but not that great. So the benefit from that for us as an attacker is that we can write arbitrary data to the price tags if we're in the proximity of Bluetooth Low Energy. So that means 20 meters or something. And the nice thing is we can just use the app from the manufacturer and walk into a competitive store and use that app to change prices on the shelves. So that's quite nice. So let's continue. And now we want to look shortly at the connection between the phone and the web server, so that we maybe can interact with some stored data there. I mentioned it's a Flutter application, and we don't have currently the capabilities to look into the code, because it's not that nice readable. So the first thing is easily we did strings and found some endpoint in there. And then because it's HTTP, we could just use TCP dump and look into Wireshark and look at the traffic that is being sent back and forth and try to understand which protocol is talked. And and if we now say we are a store owner and have this beautiful app and now try to change some prices, and then we as an attacker can think, oh, let's maybe search via the API for existing tags. So we can just use this substring search to search for all tags that start with that MAC address you can see there and get a response. And then we might select the correct tag from the store and say, I want to know what the data is on that. So let's send this post request to get the data. And then we might continue using a put request and change the data that is stored in the database. And then the next time the store owner will visit this, visit this app, he will see this beautiful new message that we intended for him. And of course, if the attacker wants to, we can also just delete the contents and have the default text on that. So that's quite nice. So to put this together, we have arbitrary read for every price tag content that is stored on the database or ever saved to this price tags. For every user out there, we can write arbitrary data to the database and change these contents, delete them, and also interact with the templates that the store uses, because you don't want to put the same layout or reconstruct the same layout for every shelf label again. So we use templates, and we can also delete them and interact with them. So we have this beautiful arbitrary write via Bluetooth and via HTTP. So that's quite nice. To the disclosure process, we of course contacted the vendor and said, hey, you have some issues there, and sent a follow-up email. And then, yay, we got a response and asked for some clarification and also for a dev meeting so that we can maybe talk to the development team and give them some suggestions on how to fix that. We were very happy about that and sent some meeting times over. But sadly, a few months after, we still didn't get an answer, and we're quite sad that nothing really happened there. It was quite bad.
So let me give Marius a hydration break and introduce the next vendor. I will just call it Sanico. They have the slogan "Smart than ever." I think there's the first typo. This should, from grammatical point, be "smarter than ever." We came up with a new idea and say "never smart." You all will also see in the next minutes why we chose that. Also, a company located in China. They advertise with even bigger numbers in terms of selling and companies and supermarkets that are where these price tags are located. And also you will notice some of these labels, I guess. Then some words on how this journey started for this vendor. We ordered some tags. These tags that communicate via Bluetooth, and then alongside them we received an access point. This was not intended, but now we had an access point that could talk to different tags. So what we did is then bought some more tags that can communicate with the access point. So you need these extra tags that communicate via different protocol at around 2.4 gigahertz. And now we had 3 things from them, so Bluetooth tags, access point, and then different tags for the 2.4 gigahertz different protocol. And then what we also received from them was an email with credentials for the web application. That was interesting, nice web application that might be good to manage. And we looked at it and saw, well, the username followed a very generic incremental structure. And then the password was a day when we received these credentials. And I think you all can start to know where this could go. And okay. And then I'll hand back to Marius.
Yeah, so again, we received an Android application, which is quite nice again. We received the price tags and also the access point with a different type of price tag, which we will talk about in a second. The components changed a little bit. We have now an additional REST API added to the web server, which essentially allows us to maybe connect some asset management platform to this price tag infrastructure, and also manage them via web UI and not only via the app. So that's quite nice. Again, we start by looking at the BLE traffic, and we have a little bit different, let's say, mechanism to update the tags. We still have to search our proximity for price tags, and then we can use the barcode that are on the price tags to scan the number, select the product code from our database, and a template, and then we can add them to a queue of jobs that are waiting to be sent to the devices. You can see waiting 1, and now if you're ready, if you're in the proximity of these price tags, you can just press send, and then the data is sent out. And of course, we again had the Wireshark traffic of that and reconstructed the protocol. Here we were a little bit more confused about the beginning, but then we saw this second path where we have 32 bytes being sent back and forth, that may be some authentication mechanism, so that would be quite nice. And then of course we have again the page data that's being sent, so that we know already. Then of course we still started again with the Android application, JetX, find the entry point, still Flutter, so unreadable data. The only issue here was we had to now reverse this Flutter library because the Bluetooth communication and the REST API communication both were in this Flutter library, so we had to start with that. So let's go for it. The thing is, if we now open this Flutter object or a Flutter file in our binary ninja, for example, and we just see some intermediate language stuff, and we can't really figure out what to do because there are no debug symbols, nothing nice to work with. We don't know where to start, which function does what, so that's not that good. So we used Flutter, which is an open source tool for reverse engineering Flutter applications, which uses the Dart runtime to give us annotated assembly compared with some Dart intermediate language, which is then quite nice. And we executed the Flutter tool, and then after a while received this beautiful code there. And the nice thing is we now have a function name there, so that's good. And then in the assembly we can see that there are a lot of function names in there, so we can really shift through that. But the thing is, we are not some superheroes who can now, use months of our time to shift through that files, get through every function and reverse that. So we used AI to translate all that code, into Python code to get it more readable and to really enjoy it reading. Still had to shift through a lot of files, but then we came up with the protocol. First, we have some setup stuff, so we get the battery voltage, which is later used for the battery percentage, and then we get a version string, which are quite nice because different tags may have different capabilities, so to get some information about that. And then we have an authentication challenge, as we guessed, get a requested, get a non-spec, encrypt it, and send it back. And this is nice, so that's good, better than the previous manufacturer. And then, of course, again, we have the page data that's being sent, so that's good. So what we have here is a normal challenge response scheme where we have essentially two devices. We have, for example, a phone and a server, and they have a pre-shared key, let's say. And then the phone, for example, says, hey, I want to authenticate our session. The server gives us a challenge, and then we can use our key and encrypt that challenge, send it back, and the server then just compares his calculated encrypted data to the one that's being sent back from the device. And if they don't match, and we then send privileged commands, we get an error, and if it's correct, then we can, for example, update the pages or the image on the price tag. So the question was, where does this beautiful key come from? Normally you would need some kind of key exchange or some other protocol scheme for that, because it's pretty hard for devices like IoT devices to get that kind of key exchange and learning. And the thing was that we shifted through the code and sadly found this beautiful static secret key, which then is just static on the Bluetooth tag and also in the app, so we could just extract it. This is of course not the correct key, but it's in there, and we can then use that to encrypt the challenge. And I don't know why, but it's okay, it's easier, but they did an effort in implementing some authentication scheme. Again, it's broken. We can overwrite the contents if we are in proximity, and also send commands like, for example, let the LED blink, but we have 2 bytes of data for milliseconds, and we can really let the LED be on for, I don't know, multiple weeks. So we can really drain the battery with that and make the price tag essentially unusable after some time, which is also quite nice. Okay, then the second thing we looked at, of course, again, the HTTP endpoints. For that, we used reflutter because we learned from last time we don't really just want to do some TCP dump, maybe. We want to just inject a proxy into that, so we can look at it in burp suite. And yeah, we could then just look at the API, play with it a little bit, and found that it was quite secure, so that was really good. We were happy about that. Props to them. But then we looked at the REST API and the management interface, which essentially looks like this. So we have this interface. We can, we can edit the products. We can, for example, queue new jobs and look at the price tags we own and can work with that. So the first thing I want to talk about again is like this sequential usernames that we had, like Jakob just mentioned, and the default passwords. And with that, it's pretty easy, as you might have guessed, to take over some accounts in the store if they don't change their username or change their password. So this is, not a good start. And then, as any normal web application pen tester might want to do, they look at the settings page and this URL and see the store ID in there. And then we just change the store ID and had the access to the settings page of the other store, which we didn't quite get because every other page was really quite good secured. We couldn't do that, but just the settings page, the most weak point of this whole application, was able to, we were able to access that. So we were able to look at the settings, change the store settings, and also re-enable the API, which is important for later, if it is disabled, and also extract the API key, which was quite nice for us. Then we found a file upload vulnerability because we could just upload arbitrary files as long as they start with the magic bytes of an image. And we could also, sadly, no PHP files, but any other files. And for our last presentation, we actually uploaded a nice vulnerability bingo to the platform. So used the HTML page to upload that. We could also, upload some JavaScript or something and get a path traversal with that also quite nice. And sadly, about 2 weeks ago, the manufacturer decided to nuke their whole production environment and delete all the customer data. And sadly, we were not able to give you that bingo today because we don't have access, and every other account we know existed is not there anymore. So that's really quite bad for us, for the talk. But big problem there. Of course, back then, they also had this nice API documentation with the sign parameter, which is essentially some sort of API key. But we thought, we saw that API key before, and we looked at our settings page, and then we compared those two. And I don't know why, but they leaked essentially most of the part of our private API key from our store. Just this one character was not included. And then we tried to look at other stores and their API key and found out that essentially the API key was the same for every store there. So we could just use our API key to access every other store's data, and we are not able to change the API key. That's important because it's statically, so we can't do anything about that. It's hard-coded. By that, as you might imagine, even if they have the API disabled, we can enable it again, create a user for their store, and interact with them, and for example, also queue image updates via the REST API, and then the normal store worker would go around, look on his phone, and execute the jobs because you don't see any details about that, and then we have a remote write. Of course, everything's unencrypted, HTTP, you might have guessed. So we have a full account takeover with multiple ways we can do that. We have this arbitrary write via Bluetooth. We have remote arbitrary write with this one-click requirement from a user. So that was quite a nice journey and pretty easy.
Yeah, I know. So now let's look at the 2.4 gigahertz technology. On the right side, you see left side, you see the picture from the vendor, and on the right side, you see one in the wild. This is what it looks up close. So if you see it in the supermarket, it might be just a regular Wi-Fi router, or it's a 2.4 gigahertz tag access point, depends on what you're looking at. Now, the big question is, what does this 2.4 gigahertz even mean? Generally, 2.4 gigahertz is just a frequency that is often used for like mid-range protocols like Bluetooth, Wi-Fi, Zigbee, but it could also be a microwave. microwaves also use 2.4 gigahertz. So the question is, what actually do the people mean when they say 2.4 gigahertz with their ESL tags? One good starting point to find out the actual protocol being used is the FCC page. You probably heard of that already, but if your device emits some radio frequency and can be sold in the USA, they have to file such a document, and there you see exactly what they are using. It's like 2.402 to 2.480 megahertz or gigahertz. This is exactly the frequency being used by Bluetooth, low energy, and Zigbee. So we probably are dealing with one of these two frequencies. Now, continuing our journey, looking at the access point, we face several problems. First thing is, we didn't exactly know which model we are dealing with from the vendor itself, and also we didn't know which protocol we are using. So if it's, for example, just plain Bluetooth, you can use some Bleak, for example, as a Python library to look at what is being emitted there, and then you can actually better see what's happening. This doesn't work here because it's not just like an out-of-the-box protocol. So the first puzzle we needed to solve is which access point do we actually have, and we found that we are probably are dealing with the eStation AP04 or later from version perspective, because the back of the access point changed there, but it's still not a lot. With that, we could look at more documentation and see the protocol in those diagrams. It says BLE, so we are probably dealing with some modification of Bluetooth low energy for this 2.4 gigahertz access point. The thing is, we have looked at other Bluetooth tags before, but in this case, the architecture is quite different. And also the use case differs. Because we have an access point, it is easier for a shop to change the price tags. No one has to walk around the aisles and manually run around and change the tags. You can just do it remotely and push all tags at once. That's nice for bigger stores. Probably this is why supermarkets are using this technology. So first, we don't just have an access point, we also have a management server, which we learned from the documentation uses MQTT to talk to the access point. Then we have two interfaces used for the access point itself, network connection to talk MQTT, and Bluetooth low energy to do initial config stuff. And then we have the last part, the 2.4 gigahertz ESL tag. So what now? We have our like some preliminary information, and we have to start reversing now. We could not find any software on the internet for the access point, so the next thing we just try to do is look at the network traffic that is being sent out by the router or access point, and we saw some HTTP connection, nothing really interesting, but we also started a port scan on the device to see what services are being exposed. And what we saw there is on these lines you see it's SSH, which is just common practice. This is totally fine, but also ADB, which is the Android debugging bridge. If you don't know, it's used usually for connecting your PC to your Android phone and get a shell there to do debug stuff like regular programming stuff. But in this case, it just instantly gave us a root shell on the access point, which is quite helpful because this way we could see what we are actually dealing with, like this small Linux embedded device with ADB SSH and a .NET app. So .NET is usually used for Windows development. In this case, it runs on a Linux device with an extra runtime for it. But also this app being .NET is quite handy here since it's very easy to reverse. Similar to Java, you can just put it into a program, in this case DNS Spy, and get out really, really beautiful source code, basically lossless from the original source code. Just the comments are missing, but this is fine. This is also already plenty to work with. And with this, we could figure out what the access point is actually doing. So we came up with this beautiful diagram. On the top, you see the BLE interface, which is used for setup stuff in the beginning. Then we have an MQTT client, also being able to do setup stuff and also pushing out commands to the serial interface, which is then used to write on the ESL tags. Yeah. So now let's look a bit deeper into the Bluetooth interface. We had several problems with the implementation. First, it didn't have any authentication and it couldn't be turned off. So anyone walking into the store could just change the settings of our access point, which would be really, really annoying. But it gets better because the developer already mitigated this issue by breaking the BLE interface. It was not functioning at all. Yeah, so we just have to hope that the default config is working and we can connect to it via MQTT. Otherwise, we would need to use our root shell to change the config. But I guess this wouldn't be the intended way. Yeah, so now let's look at the MQTT interface. This one is working. And it is authenticated, but it uses really, really weak credentials. It's along the lines of admin from the complexity. Yeah, you can use this to, as I said, change the config and issue commands on the access point and write things to the ESL tags. Here's an example of that. And yeah, now let's come to the Bluetooth, the serial interface, the interesting part for us, because if you remember what our goal is, we want to write to the ESL tags, and we want to do it arbitrarily. Yeah. So generally speaking, this is a stateless protocol. There's just being broadcasted over the air. It looks like this. Nothing interesting, or not much interesting, except the two parts with the nonce and the key, which is quite nice because it's authenticated with a key. And it also uses a nonce to protect against replay attacks. So we can't just record someone else writing to the shelf labels and rewriting the same command later again. Right? No, because there is a key, but it doesn't do anything. It's quite weird. I don't know why it's even there. You can't change it on the ESLs itself. You can put any value there on the access point. It doesn't matter. And for the nonce, it also doesn't protect against replay attacks because the tag itself just remembers the last nonce being sent. So if I push the same command twice, it doesn't work. But if I send the previous command, I can just write again. So yeah, nothing helpful there. This is what an entire workflow looks like. We connect to our MQTT server with the access point. We send our message out, and the access point then sends the bytes back to the ESL, and we write whatever we want on it. Yeah. So let's come back to this diagram I showed you in the beginning, where we have all these interfaces. From an attacker point of view, the interfaces are always the most interesting parts because this is where we can interact with the machines. So we'll just go through each interface and see what is broken there and why it's bad. So first off, Bluetooth low energy. Luckily, there are no vulnerabilities there because it doesn't work. Then the next thing is the network interface. If you are on the same network as the access point, you're instantly root because ADB is exposed. Don't do that. Just use an authenticated protocol to get a root shell on your device when you're not in a production environment. Not great. The next thing is the 2.4 gigahertz technology. And since we learned it's not authenticated, it doesn't have protection against replay attacks, we can just do whatever we want again. I can walk into every store that uses this technology and just write whatever I want on all tags. This is as bad as it can get. So maybe try to add some authentication or pairing that not everyone can just walk in and write whatever they want on it. Here is a short video of what this might look like. I can just walk in and instantly overwrite it with whatever I want. Okay, yeah, cool. So then last thing, we look at the MQTT interface. This is a bit of a weird one because the management server like if we consider it from a security point of view, should be higher privileged than the access point. So it would be really nice from the access point's point of view to pwn the management server. But since everyone implements the management server themselves, we can't say anything from this side. But from the other side, we just have an RCE. This is quite bad because if you remember, we can edit the settings of the access point, and one part of the settings that you can edit just gets inserted into bash directly, and we can just like use our typical bash injections to do whatever we want as root on the access point, because the program is of course running as a root. Yeah, so that was as much as we could find out from a software point of view. We avoided hardware reversing as long as we could, because it's much harder to do. In software, you kind of can still see what's happening. In hardware, that's not the case anymore. It's really frustrating. But our initial goal of just changing price tags everywhere would be much nicer to accomplish if we don't have to bring our own access point, because this is the case right now. We would have to walk into Rewe or whatever with our access point and connect it to a power cable, and then we can ride it. Yeah, so now I hand over to Jakob.
Thanks. Yes, so as Konrad already said, if you remember, for the Bluetooth tags, we could fully circumvent the intended way, and we didn't need the app to push anything onto the labels. But here we currently need the access point. We could circumvent some steps on the access point and just use the serial interface, the serial port, but yeah. And so we asked ourselves, can we maybe understand this protocol via the firmware of any of the chips inside the access point? So can we dump anything there, or can we maybe man in the middle while the access point is sending out data? And for all of that, we had to disassemble the access point with the risk that it might not be working afterwards anymore, because also we didn't have very much experience in hardware reversing then. So yeah, we thought some time, but then we decided to open it up. And for us, it was a little bit like Pandora's box, but this is what we saw when we loosened the screws. And you see a lot of boards, a lot of chips put on each other. And yeah, what we did at that time is that we wanted to get an idea of which chip is capable of what actions, or is, which job is intended. And so yeah, we looked up a lot of documentation or tried to find these chips and then just get some idea of a bigger picture. And we came up with this diagram that shows the different chips at the level of like who are they talking to, or who talks to them. There's this main chip, the rock chip, that's located here. That's also like to think of, this is the chip where we had the root shell on, and then we found some similar chips, or a couple of them. Those were the chips for the antennas. And they were accessed by a multiplexer, 4 of them. This is this WK here. And then if you look at the board, yes, so these are the chips, and you see the black cables. These are the antennas, and then they are fixed at the with these black stripes that they hold in place. And you see six antennas. So what was our next step? These chips or boards, there are debug ports, so there are different interfaces here. You can see 2 of them. On the left side, it's a JTAG interface, and then on the right side, classical UART. And you can use these interfaces to read and write to the chips. And so we got some info, tried to read some documentation, and then tried to connect. But on the first meeting, it failed, and yeah, I think you already see what might be the problem. We didn't have the best equipment, so we came up with some ideas and tried to hold the pins in place and so on. But here we could definitely not say that we might not be the issue at that point. So we bought some more stuff and then came back to the challenge. And then on the right side, you see the next time we already had some probes that you can hold in place on a magnetic plate. So yeah, the pin is connected 100% for the whole time. But unfortunately, every port or every debug port that we try to access seemed to be disabled, what is good from a security point of view at that moment, but to be honest, after everything we saw at that point, that was only a drop in the bucket. But we didn't want to stop at that point because we already invested a lot of work and also for this hardware reversing, and then we tried to go to dig deeper or go a level down, and we used software defined radio. You can see an HackerF on the left side here, and we wanted to capture the frequencies or the data that's being sent while the access point is pushing something to the labels. And this is visualized on the right side here. You can see this waterfall diagram. And you can, at the top, you see the frequency, and then we could clearly see the bursts that appear when we started to push data from the access point to the ESL tags. So the challenge we are facing now, or we faced back then, was we have this analog data, and we need to turn that into a protocol that we can then use to send the images via our own antenna. And for that, I think you want to say something. Marius built a GNU radio module for that.
So I tried to put a GNU radio for that. So I put a lot of work in it to quite understand how that works. Of course, I looked online for some implementations there, but some worked, but for our purpose, we might have a very modified version of Bluetooth Low Energy going on there. And all the applications that are out there are quite limited to the Bluetooth spec, and we would have to dig really deep into the level of that to understand it. And so we tried to write a GNU radio module, and after weeks of work and debugging, we were able to just get normal Bluetooth advertisements. But the issue here was, if we got back and looked at the chip again, that there was a lot of different you could configure preambles, you could configure some other parameters. So it's quite hard to start with the module if you don't know all these different factors that you might need. So some of you may think now, oh, just record the data that's been sent, put it in Spectrum, and sync the face, and look at the data there. But that is some stuff that we were not able to do, sadly. So there's maybe work for some of you here, but that was been a lot of more work for us. So we didn't do that, Responsible disclosure. We did not initiate it yet because we have been working on the access point until very recently. We put a lot of work into it, but sadly we were not able to replicate send out the data with our HackerF. But still, I mean, the application itself, the web application, cannot be used anymore currently, so that's fine. And the thing is also the first manufacturer, PixSmart, and also Zetasonico, they both don't have the ability to update their price tags or the firmware on their price tags. So there's no way to push an update onto that. So at least the price tags that are out there and they're already manufactured, they will be have these weaknesses forever. So they're quite we can't really change that. So we will go do a closure very soon, hopefully, but we don't hope for much from that manufacturer.
Yes, let's conclude some things we saw in the last 40 minutes. So to be honest, we were able to write arbitrary data to every ESL tag that we analyzed. And yeah, all of the apps that we looked at were broken, all of the tags were broken, and the access point was broken as well. So there were vulnerabilities all over the place, and that led us to some questions, or that we want to give some takeaways, that if you or if as a vendor you put these some things into your system, then be aware of what are they capable of, what services do they offer, is it necessary to offer that service, in what kind of network are they, do they have to be in the same network as some other management platform or so. And yeah, as we already said, this software is not usable any longer because they deleted the Docker container, or I don't know. And this point is like, okay, who owns or manages your software? So we did just research, and it's nasty for us, but it's not the end of our store or so. But if you have a lot of price tags there, and you have a lot of templates and schedules and whatever, then now everything is gone. And also these price tags, you cannot use them now anymore. So we can use them because we have the script to write to these Bluetooth tags in Python, but the app is not working anymore. So now it's just, I know in Germany you would say Schrott, Elektronikschrott. And and then we have an appeal to manufacturers. So there are only a few bug bounty programs for IoT products, and it is very expensive as a researcher or private researcher to get these products, and we are pleading to give researchers easier access to these products, to look at it. And now I want to come back to the beginning of the ice cream. Our mission was to maybe get a cheaper ice cream, and we were able to change the price on the ESL tags, but as we discovered, they do not change the prices at checkout, and here in Germany you have to pay the price at the checkout and not probably what you wrote on the ESL tag. Then we want to give some big shout outs to Niels and Lukas from CIMO. They helped us all along the way, and Niels is also talking here tomorrow, so make sure to listen to the talk. And if you have any questions, then reach out to us. Thank you very much.
Yeah, thank you so much. Are there any questions in the room? Oh, I already have one.
Thank you for the great talk. It was really fun, and to see that there are still so many products that can be so insecure. My question is, have you tried or looked into this UART connection between this multiplexer and these radio transceivers? Would it be possible to man in the middle that connection and use directly that one instead of GNU radio?
Yeah, so the problem is that, we could sniff that data, but essentially we already know what is being sent out via the serial port. We just don't know what is happening on the 6 different antenna chips. So I don't know why, maybe it was cheaper. They decided to do this with 6 different chips and then put the data to all of them, and we probably should have to, or we would have to look at the firmware that is on these devices. But sadly, they had no external flash, but yeah.
Yes, my question was if you could directly use these devices instead of building your own GNU radio.
Yeah, this would easily be possible. We know what we have to communicate to the controller, so we could just solder out these boards and run into the store with the boards. That would be totally possible, but we wanted to do it with our own antenna. But this would be an option, yes.
Thank you.
So as the previous audience member said like, it was a great talk. Like, thank you, it's super insightful. I was wondering, you may have already mentioned this in the talk, but I would like to perhaps know, how did you identify the different components in the hardware, like figure out this is the CPU, this is the memory management unit, and so on?
Yeah, so most of the times there are the name of the components on the chips themselves, so we try to look at as good as possible. We had like a looking glass, and we looked at it, and then we could just Google the names. But for some components it was very difficult because they, I don't know, tried to put them off and tried to put something on them. So in these cases, I myself don't know what to do, but in our case, we had a lot of components that had the name on them. We also tried to, one component was SRAM, and we desoldered that because we didn't quite look at the documentation and thought it was Flash, and then tried to dump that, but it was RAM, so it didn't work, but lessons learned. So you just have to look and hopefully guess on that, and some components have very characteristic layout, so then you would know that too.
All right, thank you.
Okay, so returning to question about modules, I think that theoretically this module can be like standard and has a standard firmware. So like since these chips are shipped to factory as a module, and since they have locked the firmware to read, which means other security level from all the other components. I expect that this modules was manufactured and programmed on other factories, so you can try to find the documentation right for this module, and it's even possible that that in documentation will be written a full description of protocol, or this protocol will be even standard. Did you try to find such documentation?
Yeah, so we tried to Google a chip, of course, we found it, but the issue here was that the platina that was used, we did not find the exact same layout. We found the chip documentation, of course, and we saw that they all have this capability of sending Bluetooth out. They have the option to configure some preamble and stuff like that.
Yes.
But yeah, the settings, the deep settings that they were configured at the manufacturer, we of course don't know. So therefore, that we would have to dump the flash from the MCU itself, and we were not able to do that. Yeah.
So the idea was not to search for documentation right for chip, but for the module. So usually such modules have a model number written on its PCB, and they usually shipped with a standard firmware from module vendor.
Yeah, I think we try to Google every name and find about all this stuff, but we did not find a name for exact that platina. Okay. And we thought, of course, that maybe it was a custom thing that was developed by them, because they used 5 chips that were the same and one that was different. That was the setup essentially kind of weird. Some had the SRAM on them and some don't. So I think that was very put together by them, and we couldn't really find something out there. But yeah.
Okay, thank you.
For the 10K tomorrow.
Yes.
Already practicing. I was wondering, have you considered how much time you want to invest for this research? Would it be possible to read the firmwares of these chips by glitching them on a regular basis? Have you considered that, or are you saying, well, I'm just done? Technically, it would possibly work. Any consideration on glitching?
Yeah, so of course we Googled a lot and came up with different variants of try to access that flash, but we are not skilled enough for that currently, so we did not try that. But of course there are a lot of ways to do that, and if you're an experienced hardware reverser and and know a lot of things to do that, of course. But we put a lot of work into it until now, and for us we're kind of through with it, because after some time it's you're just seeing the same things and get very frustrated. But a good idea. Yeah. Thank you.
Right. Any other? Oh, yeah.
Have you checked if there are any resellers who sell the same hardware, maybe with different apps or different servers?
Yeah. So funny thing, the first manufacturer we started, or I started ordering price tags from eBay and price tags from AliExpress, for example, and got them. And the first reseller on eBay was white labeled, and I got them, and they both were the same price tags from the same manufacturer. So yes, there were a lot of white labeled resellers out there. For the second manufacturer, we got the price tags, there were different ones, we got them, but the management interface or the software for the management was also a white labeled software that was produced by another shelf label producer, but we have no clue what say labels they sell, but the software, at least for the app and also for the web management software, was the same. So there will also be a lot of reselling, and we would guess that a lot of them use the same hardware or the same software. We use them, of course, but so yeah.
Well, what I wanted to remark, first of all, thanks. It was very interesting research. But following this and having seen quite another set of presentations here, what is a red line through all of it is the shoddiness or low quality of work on the sides of manufacturers protecting IoT things in general. Here in this case, German legislation is in the way, so you couldn't really do havoc with changing the labels, though it was very interesting research. I wonder what there should have to be, how to put it, minimum standards, not necessarily as over-engineered as the one for the smart meters in Germany, but still. What is your opinion on that one?
I mean, it's, especially for the key exchange, for example, it's quite hard to implement that in a correct way for IoT devices. There are so many parameters that go into it. We have the energy, the limitations. We have like the thing if we use the keys, how can we reset the interfaces? But for that, there are a lot of different ways to implement that. So at least, for example, you could put a button on the back, and if you just press the button, you could re-authenticate again or make a new key exchange. So that's like there are ways to do that and to make it harder for attackers to do that. But yeah, I mean, with the CRA coming and stuff like that, I hope that a lot of manufacturers will think about that. Maybe not the ones we looked at, but it's hard to implement that securely. But they should at least try to do that, because both of them didn't put a lot of effort in it. So I think it is possible to secure them, but it's hard, and you have to put the work and money in. And if it's just you go for the large amounts of that you sell and want to do it cheap, then of course you get that result we just looked at. Yeah. Thank you.
All right, any other questions? Otherwise, let's give a warm round of applause again.
Thank you.